In this video, we will cover section 14.2 that deals with limits and continuity of multivariable functions, and we will concentrate on functions defined in 2 and 3 variables. Okay, so this is a sketch of a function defined in 2 variables, f of x, y is equal to z. Okay, the idea is whether when we are approaching the point a, b, how much is the limit, to what value the value z appears, or comes closer and closer. Okay, now if you compare this to single variable calculus, when we were looking for the limit of f of x, let's say that this is y is equal to f of x, when we were looking for the limit of f of x as x approaches to a, okay, because x was one-dimensional, the domain was one-dimensional, we could approach this point only from the left and only from the right. Things become significantly more interesting in functions defined in 2 variables, because now the point where I'm approaching the function f is basically a point defined in 2 coordinates, right, a and b. And now I can approach this point for infinitely many paths. Basically any function, any path that crosses through this point, right, is a path that approaches this point. Okay, and that will change completely how we observe the limits in 2 dimensions. So let's just start by doing different examples. The first example is going to be where the limit, the point where we're approaching, right, is part of the domain of this function, and in that case we simply evaluate this function at the particular point, right? So again, I'm going to repeat, if the point 1, -1 is part of this domain, then let's just simply evaluate how much is this. So x is 1 cubed minus 3 times 1 squared, y is -1 times -1 plus 3 times x 1, y is -1 squared minus x is 1 over -1. Sorry, right? So x approaches to 1, y approaches to 1. Obviously, this function here is defined for the point 1 and -1. As a matter of fact, just glancing through this function, I can see that this function is not defined only for the values where y is equal to 0, so for all the values on the x-axis, but 1, -1 is not on the x-axis. So basically I can just evaluate this function, how much is going to be at the point 1, -1. So what do we get? 1 plus 3 plus 3 plus 1, and that's equal to 8. Okay, so as long as the point towards which we are approaching is part of the domain of the multivariable function, all we do is we just plug the values for x, y, z, and so on and so on. Okay, so let's see in the second example. In the denominator, is the denominator going to be 0 when x is 2 and y is 1? 4 times 2 is 8. 3 times -1 is 3. So the denominator stays away from 0, which means that the limit of this function as we're approaching 2 and -1 is going to be calculated just by what some of you are calling it from Cal 1, direct substitution. So I plug 2 for x and -1 for y. 4 times 2 minus 3 times -1, that's 4 minus 3 over 8 plus 3, that's 1 over 11, if I didn't make any mistakes. Okay, now let us start with the problems that are slightly more interesting, and those are the problems where we're approaching the limit, we're approaching the point that is not part of the domain. For example, this function is not defined for any of the values on the y-axis. Why? Because it's not defined for any x being equal to 0. All of those points lie on the y-axis, right? So that means that the origin, obviously, it's part of the y-axis, or simply I cannot plug x is equal to 0 here because I'll divide by 0. So what do? Well, in the first few examples, we were just going to concentrate on techniques learned in Cal 1, right? If I can simplify this expression, first of all, Okay, so this is going to be x squared y cubed minus 1. I factor the common factor in the numerator, divided by 3x squared, and then cancel these two. You're left with the limit xy going towards the origin of y cubed minus 1. And now this function depends only on y. Plug y is equal to 0, 0 minus 1 is negative 1. So the first idea is that if you can simplify the expression, if you can cancel the factor that's causing the problem, that's what you do. Okay? The second example is also an example that's not defined at the origin. Why? Because we cannot divide by 0, 0 plus 0, as xy goes to 0, 0. Right? But here I want you to recall that the limit of sine of theta over theta, where theta approaches to 0, this limit is equal to 1. And as you can see, this expression here is equal to theta that goes to 0 as xy. As xy goes to 0, 0, theta goes to 0, so this limit indeed is just 1. Another idea about limits from Cal 1. Okay? This is another example. Some of you might have seen this in Cal 2, as a matter of fact, or even Cal 1, 1 plus a over x to the power of bx. As x goes to infinity, this approaches to e to the power of a b, right? Some of you might have even defined the number e as this. Okay? So that's exactly what's happening here. As xy goes to infinity, this one goes to infinity and this one goes to infinity with the same rate. So this here simply approaches to, so I have 1 plus a over this expression going to infinity raised to the same expression going to infinity. So that's why this formula is just equal to e to the power of 3 times 1, which is e to the power of 3. Okay? In part f, again, I have a function that's not defined at the origin because I cannot divide by 0. But this one also asks us to do to use a technique, a thinking that we used in Cal 1. That's called the sandwich or the squeeze theorem, right? So square root of xy, as x goes to 0 and y goes to 0, goes to infinity, which means that 1 over, goes to 0, sorry about that, which means that 1 over square root of xy, as x goes to 0 and y goes to 0, goes to infinity, right? So that means that I cannot evaluate, I don't have the limit, this limit here doesn't exist, right? Because as this goes towards infinity, I cannot capture how much is sine of that, okay? Why? Because sine always bounces between negative 1 and 1. But that notion, the fact that sine of 1 over square root of xy, it's always between negative 1 and 1, no matter what the value is for x and y, basically solves this limit using the squeeze theorem. Here, if I divide everywhere by x squared, I get, so if I multiply by x squared, I get negative x squared less or equal to x squared sine 1 over square root of xy less or equal to x squared. But now as x goes to 0, this term goes to 0, right? And this term also goes to 0, which implies that this will also go to 0. So by the squeeze theorem, this limit is simply 0. Okay, so this is these are similarities between finding derivatives in finding the limits in multivariable calculus and single variable calculus.